You know, I've always been interested in nanomechanics. I started in nanotechnology in '83 at IBM, and then I moved 2001 to UCLA, and I started to think we can use this nanomechanical tool as a unique way to look at biology, and that led me into, you know, medicine. And it's absolutely an essential tool, and it keeps getting better actually, and it gets faster, more automated. So I have a rosy kind of view for the future of its use in medicine. We probably were the first to actually pioneer the idea of what is now known as mechanobiology, that is, studying the mechanical properties of cancer cells as a potential diagnostic tool. I would say that one of the beautiful things about AFM is it's a mechanical tool. It allows one to, you know, equivalently like a doctor would feel the skin of a patient or tissue, it allows you to do that on the nanoscale, and it's pretty unique in that respect. There are subtle differences in certain morphology and so on, cancer cells, but it's not always possible to tell. We have an orthogonal tool through the mechanobiology to detect, you know, they're somewhat like 10 times softer, for instance, metastatic cancer cells than some equivalent, let's say, mesothelial cells that would be in the sample. I've been working with Jianju Rao, and he's the head of pathology and specializes in, you know, cancer diagnosis. And together, we're actually working on a new type of tool, an automated platform that would allow, for instance, medical people to actually use the microscope and automatically detect cancer cells. So that is the long-term goal of our work, is actually to translate that into a medical setting. But I think also in imaging and high-speed AFM, you know, we've been able to image molecular motors running along actin filaments. High speed allows you to take videos of, you know, life at the nanoscale. I want to see the speed keep increasing and increasing way past, I think, you know, at the moment, just some small demonstrations have shown 1,000 frames a second is possible under some conditions, but under all biological conditions, if we can have really fast video and watch the mechanics of life in motion, I think that's one direction. The other direction is that AFMs tend to be general purpose. So, you know, they can look at cells, they can look at strands of DNA, so they can do lots of things, but that comes with a price. And I would like to see more purpose-built AFMs, say ones that can map DNA, that are designed for that. I think, as I mentioned, in the field of you know, medical diagnosis, machines that are much, much easier to operate so that a medical technician could run them. I think those are two directions. The third direction that's pretty important to me is to be able to keep reducing the actual forces. So down to, you know, piconewtons. We talk about nanonewtons in AFM typically, but really move into very low perturbations in terms of the forces. Those are the three personally I would like to see happen, and I think will happen actually.